So good afternoon, everyone. Welcome back to Math 122. It's getting close to the end of the semester. It's coming really fast. We're basically going to learn like these two sections and then maybe one or two or three more sections after this on some integration theory. So we're really kind of coming down to the wire. Regarding your exam, that's going to be a week from today. So, because today's Tuesday, right?
Yeah.
So the exam is 1 week from today, right? Yeah, it is. So it's on April 11th. It'll be in class. Same deal as last time. The sections that are covered are written here. And we're going to review on Thursday. So what I'd like for you to do is between now and Thursday, take a look at some of these homework assignments and pick out some of the questions that you feel like would be good for us to discuss in class on this coming Thursday, and then we'll do that review. And if nobody has anything, then I'll just kind of freestyle. So that's the review and the exam, and office hours are as usual. Math Tutoring Center as usual. SI, do we have anything?
Yeah, there'll be a review session for the test. Either the date's not final yet. It'll either be this weekend or Monday.
Okay. So review session at some point before the exam. So I just want to reiterate again, not to scare you, but the content which is on this exam is a lot harder than the content that was on the first exam. So I would say you definitely need to up your game in terms of studying for this exam in order to get a similar result on the second exam as you do on the first exam, because we covered all this derivative stuff, applications of derivatives, and also a little bit of like these Riemann sums and things like that. So yeah, make sure you study up for this one, because I just don't want anyone to be surprised when they come to the second exam and they're like, wow, that was so much harder than the first one, because yes, it is. I'm telling you in advance. So that's the exam. A homework assignment has been posted, which is going to be due this Friday. That's 5.1 and 5.2, so we'll finish up the content for that homework assignment today. But I'm only going to put 5.1 on the exam because that was covered last week. So I think that's all I wanted to say. Any administrative questions before we start? Yeah. Oh, you can't open like multiple homework assignments at the same time?
No. So it's like a lot of time.
Oh yeah, I see what you mean. I don't know. I can try to maybe like combine all of the problem sets. Okay, let me write that down and I'll try to look into it. Okay, Wiley. Like a study homework. Like that's all combined or something like that. I can try to do that. We'll see. I mean, I'm definitely not a pro at using Wiley Plus, and Wiley Plus is not exactly that user-friendly, as you can already tell. So I'll try. So, yeah. Any other questions? Yeah.
Is there extra credit for this one like the last one?
No.
No.
Damn it. Well, let me think about it. I'll let you know. Okay, so the main purpose of the extra credit for the first one was actually, I mean, it's only like 2% on your exam. It was really just to encourage people to like go and use study resources once so that they realize that like, oh, office hours are not scary. It's like, you know, collaborative, study with my other students and et cetera. So that was the motivation behind the extra credit for the first one. So we're not going to repeat the same extra credit for this exam. Sorry. Other questions? Yeah.
So there's some sections they are the same sections, like 3.3 and 3.4. How did I know that I studied 3.3 or 3.4?
Sorry?
So like 3.3 and 3.4
Yeah.
are the same sections.
Yeah. Oh, I see. They're combined homework. Yeah.
Yeah, so how did I know that I'm studying the right thing that come up in the exam?
Right. So, I mean, I'm going to choose basically one question from every homework. Does that make sense? So, as long as you're studying the questions from, I mean, short of literally telling you like the exact questions that are on the exam, I mean, that's like I think as far as I can.
That's not my question.
So what's your question, sorry?
So 3.3 and 3.4 are the same sections, right?
Yeah.
So when I'm studying them, so the exam just 3.4, not 3.3.
No, 3.3 is on there. So this means 3.1 to 3.4. So that includes 3.1, 3.2, 3.3, and 3.4. Yeah. Any other questions? All right. Then let's go ahead and talk more about Riemann sums. So we've been talking about this idea of like area under the curve. So we're using that to sort of measure accumulated change. So if we have a function which describes a rate of change, such as a velocity, then the area under that curve will represent the total amount of change over a given period of time. So what we've learned recently is, well, we want to find the area under a curve which is, not so nice in terms of the shape. Isn't a shape that I have a formula for finding the area of. So what I do is I approximate it using either a left-hand Riemann sum or a right-hand Riemann sum. Okay, so the formulas are shown here, and the formulas look messy, but the basic idea is very simple. It's to say I'm going to use rectangles, and I just need to decide how wide and how tall each rectangle is going to be. Okay? So to figure out how wide the rectangles should be, we just use this formula delta x equals b minus a over n, right? The length of the entire area, you just divide it by the number of rectangles, and that tells you how wide each rectangle should be, right? And then the height, right? In terms of finding the height, the difference between the left-hand sum and the right-hand sum is just that for the left-hand sum, we choose the height of each rectangle to be the height of the function on the left side of that interval, subinterval, and then for the right-hand sum, we choose the height to be the height of the function on the right side of the subinterval, okay? So depending on what we do, we get two different pictures, which could look like one of these two, right? So the one on the top is a right-hand Riemann sum, okay, is a right-hand Riemann sum, and the one on the bottom is a left-hand Riemann sum. Okay, and of course, if our function is increasing, like this one is, then the left-hand sum is an underestimate. And if the function is decreasing, then the right-hand sum is an underestimate. Underestimate. Okay? So that's there. I think there's a homework question or two that asks you about whether it's an underestimate or an overestimate. It depends on whether the function's increasing or decreasing. But I promise you, 99% of the problems in this entire like subfield of calculus will become much easier when you draw a picture, okay? So if you get confused, just try to draw a picture, draw the function, draw the rectangles, try to like give yourself an idea of what it is that you're trying to do with the math. Express it in this graphical way. It will help you to understand what you're doing a lot better, okay? So, are there any questions about what we did last time before we move on to something new? Did we do one of these problems last time? That's right, because we had to do the quiz or something, right? Do you want me to do this one as an example really quick?
Yeah, why not?
Okay. Thanks for your enthusiasm. So what is this? Okay, T is measured in hours since the start of a 20-hour period. Okay, so this is the problem you were working on last time before class was over. And we have bacteria, which is increasing at a rate of 3 plus 0.1 T squared millions of bacteria per hour. Okay, so the very first thing that I'm going to do is I'm going to draw a picture of that graph because it's going to help me to understand what's going on here. So let me add a page so that I can draw the picture. So what is the picture of what's happening here? The picture is I have a function. Time goes on the horizontal axis, and here's f on the vertical axis. And what kind of function is this? 3 plus 0.1 t squared. That's a quadratic function. In fact, it's a quadratic function which is vertically shrunk by a factor of 10, and it is vertically shifted up by 3. So in particular, this function is symmetric. Here's 3. It looks like a really kind of a wide parabola is basically what this function looks like. And what they're asking me to do is divide the 20-hour time period from 0 to 20 into 5 intervals of equal length. Okay, so I need 5 subintervals. So I go all the way up to 20. Okay, so what I'm going to do is there's 1 interval, 2 intervals, 3 intervals, and then 4 and 5 intervals. So I should have 5 tick marks in total, so that I have 1, 2, 3, 4, 5 subintervals. Then I have to figure out, well, how long is each one? Well, there are 5 of them, evenly dividing a length of 20. So I just do 20, or if you want to think about this, this is like b minus a over n. In this case, is 20 minus 0 over 5. So each subinterval should be 4 units long. So I'm going to make my tick marks. They're 4, 8, 12, 16, and 20. So bam, part A is done. And part B says, calculate a left-hand sum to estimate the total change in the number of bacteria over the 20-hour period by dividing this 20-hour period into 5 time intervals of equal length. Okay, well, I already did the second part, so now I just need to do a left-hand sum. So, for each subinterval, so first of all, the area that I'm trying to capture is basically this area here, which is wrapped in blue. Okay, that's the area that I want to describe. And that area is going to be approximately equal to the area of the left-hand sum. So for each subinterval, I'm going to make a rectangle, okay? I'm going to make rectangles like so for each subinterval. And I just need to decide how tall they are, because I already know each one's going to be 4 units wide. So since I'm doing a left-hand sum, for the first subinterval, okay, I'm going to choose the height of the rectangle to be the height on the left side of the subinterval, because that is what I'm doing with the left Riemann sum. So here's one rectangle. And the next rectangle, I'm going to choose the height to be, again, that height of the function on the left side of the subinterval. And then again, on the left side of the subinterval, I choose to extend that height out like so. Okay, my drawing's not perfect. But nobody's perfect. That's why you gotta work it again and again until you get it right. All right, so that's my left-hand sum. And you can tell that because this is an increasing function, my left-hand sum is going to be an underestimate. But the idea here is that the area shown in blue is going to be similar to the area shown in orange. Okay, the area shown in orange, which can be written down as a Riemann sum from I equals 0 to, since n is 5, okay, we have n minus 1 is 4, so we go I equals 0 to 4, and here we put delta x times f of a plus I times delta x, which in this case, delta x is 4, right? So we go I equals 0 to 4 of 4 times f of, and a is just 0, right? A is the left-hand endpoint, so a is 0, and b is 20. So a is 0, so this just becomes 4i, because delta x is 4. And now we need to iterate over all of the i's. So we get 4 times f of 0. That's when I is 0. And then we do I is 1, so we get 4 times f of 4 plus 4 times f of 8 plus 4 times f, plus 4 times f of 16. So in order to figure out what that is, we just need to remember what f is. So since f is 3 plus 0.1 t squared, we just need to plug in here. So f of 0 is going to give me just 3, so we get 4 times 3 plus 4 times, now if we plug in 4, what do we get? T squared would be 16, so 0.1 times that would be 1.6, right? Plus 3 is 4.6. And now we need to plug in 8, so that would make this 64, which would make this whole thing 6.4, which means we get 9.4. And then plus 4 times, when we plug in 16, we get 256, divided by 10 is 25.6, add 3 is 28.6. Okay, so we get like whatever that number is, okay? You multiply those numbers together, and you add those numbers together, and you get your final answer, which, did anybody have it written down from last time?
Isn't there a 4
I thought
f
it-
to 12?
Oh, I forgot to do 12, didn't I? Thank you. You gotta interrupt me there.
Sorry, I was
Yeah, you're right. I forgot the one where I is 3, thank you. So we also need, appreciate that, plus 4 times f of 12.
Question.
Yes, what's your
So
question?
You wrote a plus I times delta x, but why did you only put 4i? Remember it?
Because in this case, a is 0. So if you do 0 plus I times delta x, the result
just did 4i.
the result is just I times delta x. And delta x is the width of each rectangle, which in this case is 4.
Okay.
Does that make sense now? Okay, so let's add 4 times, let's see. So I also need 4 times what I get when I plug in 12, right? When I do 12 squared, I get 144, so this would be 14.4, plus 3 is 17.4. Okay. So now I think I have it. So let me get it all on the screen. So what's going on with this summation notation is really just something really simple, right? The first thing, 4 times f of 0. That's the area of the rectangle on the far left. Yeah. And then we add the area of the rectangle from 4 to 8, and then 8 to 12, and then 12 to 16, and 16 to 20, right? So again, I think if you draw the picture, you can almost get away without even memorizing, like, what is this formula? But it does require you to sort of know, like, what a function looks like, which I think if it's a quadratic function like this, you probably know what it looks like. So once we add all these up, we get some number. That number is the area of all of the orange rectangles combined, which serves as an underestimate for the true area of the blue shape. So are there any questions about this example? Yeah.
So if you were to do like a right hand sum, it would just be 1 plus, one plus I times delta x.
No.
No, would it be 4?
Well, let's just do it.
Okay, yeah.
Let's see what it would look like when I did a right-hand sum. Well, what I need to do really, you can figure out. Okay, so actually, I admit to you, I don't keep this formula memorized. What I keep memorized is the idea of what I'm doing, and then I can write down the formula from there, right? So delta x, that's the width of each rectangle. And then I just need to say, well, what is the height of each rectangle? It's either the height of the function on the left side of each subinterval, which is given by the point on the left, and then we go point on the left plus 1 delta x plus 2 delta x plus 3 delta x plus 4 delta x. Or we're going to do a right-hand sum where we're going to choose the height to be on the right side of each subinterval, right? So the formula for the right-hand sum, why don't I do it with a different color? We'll do green. So the formula is I equals 1 to n, okay, of delta x times f of a plus I times delta x. That delta doesn't look good. Okay, so the difference between the left-hand sum and the right-hand sum is that I goes from 0 to 4 in the left-hand sum, and in the right-hand sum, we're going to go from I equals 1 to 5. And then it's going to be 4 times f of I delta x again, because a is going to be 0 still. So the difference is this is going to be equal to 4 times f of 4 plus 4 times f of 8 plus 4 times f of 12 plus 4 times f of 16 plus 4 times f of 20. And let me show you how it's different in the picture. In the picture, we're going to use the height. Okay, I guess I got to use maybe dashed line so that we can see still what's going on in orange. Okay, so this is the difference. So in the left-hand sum, we start with I equal to 0 so that the height of the leftmost rectangle would be what we get when we plug in 0 for I, which would be f of 0, right? But in the right-hand sum, we want the height of the first rectangle to be the height of the function not at 0 but at 4, which is why we choose I equals 1, so that when we multiply 1 times 4, we get 4 here, so that we have f of 4, which is the height of the function at 4 and not 0. So it's a difference between the heights of each rectangles being f of 0 through f of 16 versus f of 4 through f of 20. Does that make sense? So the formula is actually exactly the same. The only thing that changes are the bounds, where you start and end with I. Okay? Any other questions on that one? All right. Well, trust me, once you do the homework for this chapter or for this section, I think you'll feel a lot better about it. Every time, I always recommend you to draw the picture so that you can see what's going on. So let's, I guess, move on to the next section. And, yeah. Okay, so we're now going to actually formally define, actually we're going to extremely informally define what is an integral. So an integral from a to b of f of x dx is defined to be the limit as n goes to infinity of the sum from I equals 0 to n of delta x times f of a plus I delta x. And that's the same as the exact same thing, but with, oh, sorry, I wrote something down wrong here. This should be limit to n minus 1, and the next one should be limit from I equals 1 to n. And this is what we call the integral of the function, okay? So there's kind of a lot swept under the rug with this definition in this textbook, mainly because we have not explained what a limit is, okay? So, and it's probably not worth going that far off course to define what that is. So what do we mean when we say the limit as n goes to infinity? What we mean is we are going to take more and more and more and more rectangles, okay? And the area is going to get closer and closer and closer. So I think I already did a drawing of this like this here, right? So when we take just two rectangles, there's lots of error between the true area and the area of the rectangles. But when we take lots and lots of very, very thin rectangles, then the area becomes extremely close to the true area. And the limit process is to say, well, what if you took 100 rectangles? What if you took 10,000 rectangles? What if you took 1 trillion rectangles? well then your actual area would become incredibly close to the true area. And there's this process called a limit by which you formally define the number which all of your Riemann sums are getting closer and closer to when you use more and more rectangles. Okay, so that's what we mean by limit as n goes to infinity. What we mean is the limit as the number of rectangles becomes infinite. You can imagine that the area will actually become the true area under the curve. Okay? So that's our definition of the integral is taken to be the limit of these Riemann sums. And it turns out it doesn't matter if you do a left Riemann sum or a right Riemann sum. When you let the number of rectangles go to infinity, the left-hand sum and the right-hand sum actually become the same number. Yep.
So what does that little S thing stand for?
S.
A and B between A and, is it the difference?
Oh, this, you're talking about this symbol.
Yeah.
So this symbol is the symbol we use for integration from A to B. So it's it actually came from, okay, so you know sigma is like S for sum, yeah? This integral sign also used to be like this weird looking S shape that now we just use to say, when you write this like S shape here, this elongated thing, it means do the integral of f of x with respect to x. So the with respect to x part is this dx part, and then this part says do the integral from a to b of this function. So this literally means like if this is a and this is b and this is your f, okay, then this region in here is integral from a to b of f of x dx. Does that make sense now? Yeah, so this is just notation. And this is what it looks like if you could actually draw it correctly, which I can't. Any other questions on that? Okay, so far we don't actually know how to do an integral, but we know how to do Riemann sums to approximate the value of an integral. And we know that the more rectangles we use, the better our approximation will be. That's what we know so far. Okay, so I'm going to skip ahead a little bit. Or am I? Okay. I feel like we just did a Riemann sum problem. I'm not sure we need to do another one, do we? Maybe we do. Let me think for a minute. Okay, let's do this problem. Let's do problem number 4. Okay, so what do we want to do? We want to estimate the integral from 0 to 3 of f of x dx. So in order to do that, I'm going to first just visualize what this is. What even is this? Okay? Well, this is the true area under the curve of this function where we start counting area at 0, being x equals 0, and we stop counting area once the x value becomes 3. So we go counting all of this area until we get up to 3. And then we're going to stop counting. Okay, so a visualization of that is that we're trying to find the area of this shape. Okay, we're trying to find the area of this green shape. So basically the only method that we have so far would be to try to like make some boxes, right? So if we did a right-hand Riemann sum, it might look like this, and we'd make some rectangles and then dot dot dot, right? Make some more rectangles, and then we would get an approximation of what that area looks like. So that's one method. We're going to learn some more complicated methods later on where we can actually find the true area under this curve. But I want to make known one other methodology, which is to try to count boxes, okay? So we do this in the following way. We know that each box like this has height 1 and width 1/2, right? So the area of each box is 1/2. Do you agree? So if I were to say count however many boxes I have contained in this shape, then I would know I could take however many boxes, so number of boxes, multiply that times 1/2, that's the area of each box, and that would give me an approximation of the true area in green. Okay, so let's do that. So the way that I like to do this is I literally just look box by box and I check about how much of that box is incorporated into the shape. So this looks like one full box, you know, and let's count all the full boxes. These are all full boxes pretty much. And then this one here looks like, to my eye, I don't know, maybe like 70% of a box. So I would call this like 0.7 of a box. And I would call this 0.2 of a box. And I would call this 0.8 of a box. This is maybe 0.3 of a box. This is 0.4 of a box. That looks a little bit bigger. This one looks like, I don't know, 0.7 again maybe. This one's less than half, so maybe 0.4. And then this one's like probably 0.8. 0.7, 0.4. This one could be like 0.2 and 0.1. So I can count up all of the boxes and add them all. So what do I have? 1, 0.7, 0.9. Add 0.8 to that, I get 2.7. Add 0.3 to that, I have 3, 0.4. 5.4, 6.4, 7, 8, 9.4, 10.1, 10.5, 11.3, 12, 12.4, 12.6, 12.7. Seems like I have about 12.7 boxes.
Oh, there's a box you didn't count.
Was there?
There's a box.
Above 0.4. To the left of 1.
This 0.4?
Yeah, right above it.
Oh yeah, you're right. So 12.7, and I didn't count this one, so there was maybe 0.1. Thanks. Did I miss any others? Okay, so 12.8 times 1/2 gives me 6.4. So I would say that the integral from 0 to 3 of f of x dx is approximately equal to 6.4. Yeah.
Isn't it quite subjective though? Like, couldn't the answer?
Yeah. So, I mean, if you got anywhere between like 6 and 7, you know, if you write down like 35, then I might like raise my eyebrows and be like, I'm not sure that that is correct. But you know, as long as you're somewhere in the region of the right thing, this is not, you're exactly right. It's not an exact science. It's not an exact science. But this is one method that you can do. And usually like on the homework problems, like if the true area is like 100, the homework will accept anything between like 85 and 115. So they're built in with tolerances. Yeah.
Why would you do this and not the like right hand, left hand thing?
Because theoretically this could give you a more accurate result.
Okay.
Okay, here's why. If I were to do a Riemann sum, right, then what I would actually be counting is the area of these boxes. So let me show you. I'll just draw it real quick. So this is a left-hand Riemann sum, since I'm choosing the height to be the height of the function on the left side of each subinterval. So why is it better to do the box counting method than to do this Riemann sum? Well, you can see there's quite a bit of error in the Riemann sum, right? And you know, it's sort of you know, slightly more accurate probably to go by boxes for this problem. You know, it really depends on whether you have a graph or not, right? Because if they ask you to do the integral of like x cubed or something like that, unless you have very fine motor control, I kind of doubt your ability to like draw an accurate graph. Even if you had graph paper, it would be tough to do the box counting because you don't know the exact curvature of x cubed memorized. I mean, nobody does. So in that sense, this method is probably gives you a more accurate result, but only when you have the graph of the function like on the paper in front of you, right? Okay, another thing too would be that for some of these boxes, like on the Riemann sum, we'd be guessing how tall they are, right? Because, I mean, who's to say that this is, you know, 0.5 tall versus 0.45 tall, or something like that. So, I mean, I guess there's kind of guesswork involved in both scenarios. Any other questions on this one? Okay. So I'm going to move on to 5.3. I wasn't planning on doing this today, but I think we're going to do it. So there's not going to be homework on 5.3. But that doesn't mean you don't need to know what's in 5.3 because it comes back in chapter 6. So I want to explain to you that I've lied. Well, that's not true. I have withheld information. So what I've told you is that the integral of a function is the area under the curve. That's what I told you. And that was like, you know, it's like when your parents tell you that babies that babies come from the stork, right? It's just a placeholder idea before you're ready for the real thing. So don't worry, I'm not going to tell you anything crazy like that, but this is the area under the curve, which we said the integral of f of x is given by this area under the curve. But what I didn't tell you is, what do we mean when we talk about the integral of, say, a function g of x from a to b, when g of x is a function which is negative from a to b. So then it's a question mark what this integral really means, okay? So the extension, okay, the extension of this idea is the following. So if you call this region here, which is between the function and the x-axis, if you call this area A, which remember area is always positive, then the integral from a to b of g of x dx is actually equal to negative a. Okay, negative a. Okay, so it's possible for an integral to be negative. And here's a quick heuristic idea of that, right? Let's say that this is a velocity function. What does it mean if the velocity function is negative? That means I've got my car in reverse, or I'm walking backwards, right? And if I walk backwards for a period of time, right, then the area which is trapped between this curve here is going to represent how far I walked in the backwards direction, right? So if you're talking about like how far away I am from home, for example, right, I can move away from home, which is accumulating distance, or I can move towards home, which is like accumulating negative distance. Heavy air quotes there. So it's actually the accumulation of negative change just tells you how something is decreasing, okay? How something is decreasing, the total amount of change in the decreasing direction. All right, so now I've told you the real thing. So actually, there's maybe one more thing to tell you, which is what about a function which is sometimes above the x-axis and sometimes below? So the final story looks like this. So we go from A to B, and we could have a function which looks like this, maybe. And what we are going to do is we're going to take this area which is beneath, and we're going to take this area which is above, and we're going to say that the integral from a to b of f of x dx is whatever is the area which is above, and we're going to subtract the area which is beneath. Okay? We're going to subtract from that the area which is beneath. So I would expect, well, actually let me ask, what would you expect the value from integral from a to b of f of x dx? Do you think that this is ultimately a number? Do we think it's a positive number or a negative number based on the drawing? Who says positive? Okay, most people say positive, right? Can someone explain why you say positive? Yeah, Braden.
Because there's more positive than there is negative.
Exactly. There's more area above than there is area beneath. If you take away something smaller from something larger, then you still have something positive. Okay? All right, so let's work together on a group problem here. Okay? So for this problem, we tell you exactly what the areas are, and we just need to do some integration here. Okay, so work with a partner and try to work through these, and I'll be walking around to answer any questions you might have.
Does that say 0.75 on
Yeah,
the?
this says 0.75.
I'm gonna look back and be like, why was I writing random numbers in there?
Are you asking?
Yeah. Well,
I can't subtract fractions to save
That's what makes
life.
sense.
Like decimals.
Yeah, exactly. What about
It's,
B?
it's here and there for me, honestly. It's honestly based on whether I feel
You said 1.7.
So
The integral from 2 to 3, right?
This
Yeah.
is
Let's just go start at 2. We go to 3. So,
Oh, from 2 to 3, never mind.
yeah, just negative points.
I was thinking that is
area
like-
of D, right?
Yeah.
Exactly. What about from 0 to 3? Yeah, you're gonna take away.
Stop.
Yeah.
See what happens.
I was reading.
Or you could wait the 20 minutes.
Yes, you should be negative, right? Because we have area which is equal, we count that as negative. I mean,
Yeah.
You doing okay, dude?
So, is it negative and you want that to screw it?
How do you mean?
Goes to
Right, well,
is it for E?
so
I got a few points.
what we actually want to do is it should sort of counteract some of this stuff.
Yeah,
right?
it's
This is-
important to
this is
recognize
busy.
one.
So what we actually want to do is we would do all of the area which is above. Okay, so we're just entertaining from 0 to 3,
Is it
right?
N?
So from 0 up to 3, we're going to take all of the area which is above, and we're going to subtract from that all of the area which is beneath. So actually we get 1.75. We take away 0.75.
Okay, so you wouldn't put the negative.
Well, for this one, you would be negative because from 2 to 3, we only have area beneath, right?
Right.
So we can think of it as the area above minus the area beneath would be 0 minus 0.75, right? Because there's 0 area above and there's 0.75 area below.
Okay.
So we take away 0.75 from 0, we get negative 0.75.
Right. Right.
If we consider from 0 to 3, then we're trying to take 0.75 away from 2.5.
Okay.
Does that make sense?
Yeah. Thank you.
Mm-hmm. What are you two doing?
Not walking. I was working with.
Okay. You're done? Okay, great.
think.
Do we need more time on this one? Okay, y'all finish that really quick. So is this easy then?
Yes.
Okay, good. That means I did my job.
Very easy.
Very easy. Okay. Well, let me give you something harder then.
No.
Oh. No, let's see. So, okay, what is this? Another box counting problem. Oh, okay, here we go. This is more interesting. Area between two functions. How are we going to do that? Well, I'm not going to tell you. I'm just going to ask you. Let's say I have one function, f, and another function, g. And let's go A and B. How am I going to find the following area? which is trapped between these two curves. How am I going to find that area there, do you think?
Imagine some boxes.
Imagine some boxes. Owen, you got an idea?
The area under F minus the area under G.
Yeah, exactly. Okay, so this comes back to a basic trick that you probably learned when you, I don't know, when you took like basic geometry, which was the following. You know how to find the area of a square, yes? And you know how to find the area of, say, a triangle, yeah? So, in particular, you know how to find the area of everything of this like donut-shaped thing, right? By taking away the area of the triangle from the area of the square, right? So the area shown in here in orange is equal to just whatever is the area of the box minus the area of the triangle. Yeah? We take away the area of the triangle from the box and we get what is shaded in orange in the first picture, right? So for this one, we're going to do the exact same thing. We're going to say, look, I don't know how to find this area, but I know how to find this area. And I know how to find this area. Okay? So that's what we're going to do. So it's actually going to be, so if this is my A, then A is is equal to the integral from A to B of f of x dx. If we do that, then we've overcounted, right? We've counted all of this area. So we need to fix that by taking away the area which is under G, which should not be counted. So then we subtract the integral from A to B of G, and I should have used G of f of t dt, because it's t, and G of t dt, which it turns out is actually equal to the integral from A to B of f of t minus G of t dt. Okay, so what do I mean by that? What I mean is that if you made a new function, and for each x value, the height of the new function is just whatever is the height of f minus whatever is the height of g. So in this case, it would be something like right here, right? If you made a new function whose height is just whatever is the difference in height between these two functions, okay, then you can find the area under that new function as well. It'd be the same, right? So in other words, I just take this height here and I move it down so that it's like shown here. Yes? I copy it down to make a new function whose height is exactly, for every x value, the difference in height between these functions. Okay, another way of thinking about it would be to say that this is approximately equal to the Riemann sum from I equals, yeah, that's right, I'm going back to Riemann sums, delta x times, and what are we going to choose the height of each rectangle to be? The height of each rectangle would be f of a plus I times delta x minus g of a plus I times delta x. So what would that be? That would be a Riemann sum where all of our rectangles, why don't I make this pink and just for demonstration purposes show you what this is about. This would be like doing rectangles which look like the following, right? The height here is the height of f minus the height of g. Okay, so you could do a bunch of rectangles which look like that. That's another way of thinking about that. Okay, so the area between two functions is real simple. It's just the area which is above, or it's the area under the top function minus the area under the bottom function, if you want to think about it that way. Okay, so let's do another group work. We're going to work on problem number 5, and I'm going to give you a hint because problem 5 is hard. The 2 hints, actually. First of all, which function is quote-unquote on top? That's hint number 1. Hint number 2, what are A and B? Then, once you figure those out, we're going to do the integral of something minus something dx from something to something. All right, so that's the hint. I'll be walking around to help, and just let me know if you have questions. It's Ryan here, Aiden, Heller, Liam, Jack, Daniel Kelly, Dan O'Terry, Christopher Webb.
Wouldn't they overlap at some point?
That's a good question. Could you find out? How would you find out?
If I graph it.
If you graph it, okay. Or how else would you might you find out when are these two functions going to cross each other?
Put them equal to each other.
Bingo.
Oh, but I think
So how do you decide which one is on top?
What?
If they cross each other? Would that depend on what your A and B
No. Well, A and B are going to be where the function crosses, where these two functions cross one another, right? But which one is on top? Well, we have to take some number. We could take some number, say, between A and B, and check, well, which function's higher, right? So we take some number between A and B, plug it into both functions. Whichever number is higher, that's our, quote, top function, right?
Does it matter? So that we
Yes,
can
it
tell
does.
them to X.
Yeah.
You said x is -2.
Well, let's start with drawing a picture. What does the function x squared look like? Just like a parabola, right? And how about the function 8 minus x squared? What does that look like?
Oh.
So for y equals x squared,
Alright, let's see. No, this is.
we have a parabola. But for y equals 8 minus x squared, this is the parabola, but transformed in 2 ways. It's moved up by 8 units, and the minus sign is going to do
Yeah, if there's one,
What's that minus
it's not
sign?
getting us an amount, it's just break it up.
Flip it which way?
Which I guess we could do.
Left and right or up and down? Yeah, it's going to flip it up and down. So this is going to be a parabola which opens down. So it's moved up 8 units, so here's 8. And it opens like that, right?
maybe not.
And if you solve this equation,
I can draw a
you'll find
different
out
picture to do that motion.
what is this x value and what is this x value. You know where to go from there? Alright, think on that and see if you can make
We
it.
could just do 4 boxes.
That's true.
So then we don't even need to draw it. If we know,
Let's do that.
yeah, if we know that's 4 boxes.
No, you're right.
So for, well,
Should we do left hand?
Left hand is the one where we subtract one from there. We start at 0.
Start at 0, yeah.
Right, approximately to 3 months. But we don't actually have a way of finding it, right? But if you, like I said with her, if you want to go for gold, then try using a Riemann sum to approximate it. You choose how that directly.
What is negative?
Is it
What is negative?
You mean like left or right Riemann sum? Not really. They're both going to be wrong in some sense, right? Do you have any questions?
I'm just like trying to visualize.
I mean, it looks like you visualized it well, except the only thing I would say is it's a little bit confusing why you put -2 here, -2 here, when they're actually x values, right? Right. So you solve this equation, you get x equals plus or minus 2. I probably want to. Yeah, exactly. What about 8 minus x squared?
That's it.
And then opening down, exactly.
Wait, which one am I even doing?
Exactly.
This is just gonna get us the same answer for there.
Well, draw it real quick.
No, it won't, because you do the F of, and then that will like get those numbers figured out.
Okay, so what's the area we're trying to figure out here? It's that in the oval, right? So in terms of where we're gonna start counting and stop
No, but what I'm
counting,
saying is that we're using the same equation.
is those two x values, right?
There's no change in the equation. It's both are split into 4 boxes and both are going to negative.
Yeah, but your F is what's gonna make a difference. Like the F of, like F of 4 for this equation is gonna differ than the F
The
of 4
height
for
of the
this
function on
equation.
top is 8 minus x squared. And I want their height to
Oh,
be
because you plug it back into the original value.
Yeah.
the same.
This is a lot of work.
So we just take those heights instead of.
No, well then that means we don't need to rewrite these. Like you just need to actually just plug them in.
I'm gonna do it too.
I'm not rewriting all this shit. This is too much. My brain is gonna explode.
Are you also confused on what to put here and here? So I like your drawing. So would you be able to make a drawing like that, Olivia? Based on those pictures, right? So x squared, that's parabola, opens up 8 minus x squared, parabola, move up 8 units, and then opening down, right? So I think what we're focusing on here for our bounds is, well, where do they cross each other, right? To check that, we just set them equal to one another, which I think we did. Plus or minus 2, great. So then, from here, what we want to do is just say, well, it's not up there anymore, but what we said is that the area here is going to be the integral of the top function minus the bottom function. So here, what's our top function going to be?
8 minus
Yeah, exactly. Well, you can approximate it, but what we're aiming for here actually is just to write down this integral. So we're just trying to put it into the integral form, and for now, the only way we have for actually like computing integrals is we can approximate them in Riemann sums. Yeah.
So what do we put in here? Is just those, or how do we
Yeah,
put it
so-
into?
Exactly. So our f is the top function, which is 8 minus x squared. So that's what we're going to write right there. And then we're going to subtract the bottom function, which is just x squared. Yeah, you definitely could. You could make it 8 minus 2x squared. Right? The only thing I want to point out is we always want to have a dx at the end of your integral to show where we stop. Just
So are you doing the reward sum?
Yeah. This is, I'm like, there's so much.
Yeah.
But anyways, I did get
About 20.
All right, we're gonna stop for today there. So
I'm literally gonna be in like a.
Thursday we're gonna have the review, okay? And then exam next Tuesday. No quiz this week. No quizzes ever for the rest of the semester. But you do have an exam.
And the final.
And the final, yeah, that's true.
Oh, we just do quizzes instead.